interesting talk and a lot of questions with it. So let's go ahead with the next talk. Next talk by Debodirna Ghosh, talking about super translations at time like infinity. Debodirna, you have 15 minutes, that is 12 plus 3. I will flag you at 2 minutes before your time.
Okay.
Go ahead, Debodirna.
So can you see my slides?
Yes, we can. We can. Yeah, please go ahead.
Yeah, just a moment. Okay. Okay. So thank you. I would like to thank all the organizers for giving me an opportunity to speak here at this edition of CSGC. So the title of my talk is Super Translations at Time Like Infinity. This work is based on this paper, which was done in collaboration with my supervisor, Amita Vinmani, who is in the audience. And the other collaborators are Shumanta Chakraborty, Jahanur Haq, and Aniket Khainer. Okay. So this is the outline of my talk. So I'll start by giving an introduction and then motivation behind my work. I also will give a notion of asymptotic flatness in this introduction. In the next section, I will talk about super translations at time like infinity. And then I will talk about the IR world global charges, the contribution to the IR world global charges from time like infinity, and the associated localized charges with the super translations and the Lorentz symmetries. And finally, I will talk about, I'll summarize and then I'll conclude my talk. Okay. Okay, so I must say that most of the introductory materials were quite well elaborated in Sigi's talk. So I'll start by showing you this picture. This picture is like the triangular equivalence relation between separate theories, which tells us about that a series of separate studies are essentially the same. This is also known as the infrared triangle of Strominger. So here, what do I mean by the series of separate studies? The series of separate studies are the studies which are related to the infrared dynamics of massless particles. Okay. So the studies are here denoted by the three vertices, which are soft theorems, asymptotic symmetry, and the observational part. Hello.
Yeah. So
there's a lot of noise.
Seems to be some noise. Sorry for that. Okay, go ahead. Now seems to be a bit quiet.
Yeah. Okay. Okay. So yeah, as I was saying that the three vertices denote the separate studies, which are soft theorem, asymptotic symmetries, and the observational part, which is the memory effect. Okay. And each of these studies are related by mathematical relations. Like soft theorem is related to asymptotic symmetry by word identity associated with the symmetry. So the infrared triangle gives an equivalence relation that governs the infrared dynamics of all physical theories with massless particles. The three vertices denote soft theorems. Soft theorem essentially characterizes the universal properties of scattering amplitudes and the Feynman diagrams when one of the external particle, one of the massless external particles becomes soft. Okay. And then there are memory effects, which I'll not talk about, and asymptotic symmetries. These ideas are connected by mathematical relations. We'll only discuss about the vertex representing asymptotic symmetries. Now, the asymptotic properties of gravity have been studied quite extensively for the decades in context of understanding the asymptotically flat spacetimes at null infinity. However, the symmetry group at null infinity is not the usual Poincare symmetry group that we come across in special relativity. But the group is called a BMS group by the name of Bondi, van der Boot, Metzand, and Sachs. So this group is a semi-direct product of super translation group and Lorentz group. Under this group, one asymptotically flat solution of general relativity at null infinity is mapped into another solution, out of which the super translation subgroup is infinite dimensional, and it generates arbitrary angle dependent translations of retarded time. So now, the BMS symmetries are the exact symmetries of general relativity, we expect that the BMS symmetries should be present at special and time-like infinity. But provided that the boundary conditions at the special and time-like infinity are compatible with the boundary conditions at the null infinities. So then a natural question to ask is, how do we relate these boundary conditions at null, special, and time-like infinity? This is indeed very difficult to answer. However, Hanno and Troyside in a series of papers have proposed boundary conditions at special infinity that were invariant under the BMS symmetries. They have also introduced the BMS generators, which they have also related the BMS generators from special infinity to the null infinities also. In that context, our motivation in this work lies in exploring the boundary conditions at time-like infinity that will realize the BMS symmetries, in the sense that it has a non-trivial action on the asymptotic fields and have generically non-zero charges. So the motivation in the context of black holes comes from the recent studies of Hawking, Perry, Strominger, Carlip, and Donne et al., where they suggest that the stationary black holes also possess an infinite number of symmetries in the near horizon region. It is believed that the global charges associated with supertranslations receive contributions both from the horizon as well as from the null infinity. Thus, for a complete study of conservation laws associated with supertranslation, it is required to know the relation between the symmetries at the horizon to that at null infinity. In that aspect, time-like infinity can be used as a link between the symmetries at the horizon and at null infinity. Okay, so in the next 2-3 slides, I will talk about the notion of asymptotic flatness at time-like infinity. So our notion is based on the corresponding notion which were introduced by Beig and Smith at special infinity. So the uv theta phi or the ur theta phi coordinates or the vr theta phi coordinates are not the good coordinates to study the physics near time-like infinity. So introduce a set of polar coordinates which we call as good coordinates, tau, rho, theta, phi, for the Minkowski space. Okay, so here tau is given by this equation, where eta mu nu is the flat metric, where most of the diagonal signs are taken to be positive, and rho is given by this equation, defined by this equation. So in these coordinates, the flat spacetime metric takes the following form, where the line element is given by dA square equal to minus d tau square plus tau square times a line element which denotes the Euclidean ADS3 hyperboloid. So if I take tau to be constant, then the hypersurface will be Euclidean ADS3 hyperboloid. Okay. So now to understand this tau equals to constant slices, let me show you this diagram, which shows the hyperbolic slicings of a Minkowski space. So this is the Penrose diagram of a Minkowski space, and chi plus chi minus at the future and past null infinities, I plus I minus at the future and past time-like infinities, and I0 is the special infinity. Here, both the rates and the blue slicings are the constant tau slicings. Okay, and on the rate slicings, tau squared is greater than 0, and it denotes the Euclidean ADS3 hyperboloid. So as we will discuss the physics near I plus, the future time-like infinity, we are only interested in the rate slicings and the upper part of this diamond. Okay. Now let us go very near to I plus. Okay, so as one approaches I plus, one kind of zooms into the structure of the future time-like infinity. So this is a kind of a modified Penrose diagram. So as one approaches time-like infinity, so as one goes tau tends to infinity, one realizes that the future time-like infinity is given by, is realized as a Euclidean ADS3 hyperboloid, which is given here in the top part of this diagram. Okay, so then now we know what are the good coordinates are, how the Minkowski spacetime looks like, the flat spacetime look like. So we consider a general class of spacetime, which is defined by this metric G mu nu, and which is equal to eta mu nu plus a summation over the inverse power of tau. Here L n mu nu is this tensor at any order n will be the ratio of the Cartesian coordinates and tau. So following Bike and Smith, this metric, G mu nu, can be put in a more convenient form where the line element is given by ds squared equal to minus capital N squared d tau squared, where capital N is called the lapse function. So lapse function essentially what it does is like it normalizes the appropriate the normal appropriately. So and plus HAB, which is a three-dimensional metric to d phi A, d phi B, where this phi A and phi B are the coordinates are the rho theta three coordinates, which are rho, theta, and phi. So phi A collectively denotes rho, theta, phi coordinates. Okay, so here the capital N, the lapse function, is given as 1 plus sigma over tau, where sigma is a function of rho, theta, and phi, and HAB can be expanded near time like infinity as shown here. So the leading order term H0AB is the Euclidean ADS-T hyperboloid that we just talked about.
You
Yes.
have 2 minutes.
Okay. Okay. So yeah. So let me just say that the following, the above form is our starting point. Okay. So in the next section, I will talk about super translations at time like infinity. So super translation are the genuine symmetries of general relativity. Then they should also be realizable at time like infinity. A natural question, therefore, to ask is what is the set of diffeomorphisms that preserves the form of the metric? So this diffeomorphism, which is by these two equations, preserves the asymptotic form of the metric up to order 1 over tau. Here, the initial coordinates tau bar and phi bar are transformed to tau and phi a with this by this arbitrary function omega, which is a function of rho, theta, phi on the Euclidean ADS-T hyperbola. It also determines the higher, this function determines the higher order terms in diffeomorphism uniquely. Okay. So we only focus on super translations in our work. We don't worry about super rotations, etc. So under general super translation, the zeroth order field and the first order field sigma does not transform. However, the first order metric correction H1AB transforms under general super translations, like in this form, where dA and dB are the covariant derivative which are compatible with the metric H0AB. Okay. Now omega is an arbitrary function on the hyperboloid. It's a function of rho, theta, phi. So one needs to specify further boundary conditions to get some useful results. Okay. So the boundary conditions at time like infinity should remain invariant under allowed super translations. Now to state the boundary conditions, we define this quantity KB, which is equal to the first order metric correction H1AB plus the first order field sigma. And it follows that under general super translation, KAB will transform exactly like H1AB because sigma and H0AB does not transform under super translations. So there are two natural sets of boundary conditions that we can consider. First, we can dispose of super translations by demanding that KAB equals to 0. So if we take this boundary condition KAB equals to 0, if I go back one slide, if we put KAB equals to 0 here, then the solution omega KR will only give you translations. Then another set of boundary conditions is to take a trace of KAB, which is K, to be equals to 0. And if you take trace of KAB, that is K equals to 0, then you will find that the difference omega, the super translation function omega, satisfies this following differential box minus 3 differential equation. Okay. Now we work with nonlinear gravity. Thus we can obtain second or higher order transformations of the field. So the action on the second order field is given by this following equation, where the second order metric correction transforms to H2AB plus the terms which involves the covariant derivatives of omega and K plus the terms involving covariant derivative of omega and sigma plus the terms which are of the order of omega square. We find that these second order super translations are consistent with the Einstein's equation of motion when we split the Einstein's equation of motion in the set of three equations. Okay. So I will quickly talk about this section where I talk about the global charges and the localized charges.
Devo, you are already out of time. Can you wind up quickly?
Yeah, so I can wind up. So what we have done here in this section, I mean, this is the most, important section of our paper. So what we have done is, like, we have shown that the global charges associated with the higher world global charges, the contribution to the higher world global charges from time like infinity is equals to 0. So the symplectic flux through time like infinity is 0. So then we have defined localized charges associated with super translations and Lorentz transformations. So the localized charges which are associated with super translations are in this kind of form. Okay, so yeah, so this is what I have to say. Maybe I don't have any time to further move. Okay, if there are
Okay, thank you for a nice talk. Now it is open for the questions.
Hello.
Yeah.
Okay. Hi. Thanks. It's for nice. I want to understand one thing. I mean, if I remember correctly, I mean, there was this proposal by Hawking and I think probably Strominger. So they, when they talk about these asymptotic symmetries near the null infinity, and then they are saying that there is these are the physical symmetries. That is what you also mentioned. So so now, moment to choose a particular background, those physical symmetry is essentially broken, and then you expect, because of this breaking, you would expect some Goldstone modes associated with those. So in this particular case, I mean, what kind of Goldstone boson modes are the same, or what kind of Goldstone boson mode you are expecting, or what are the physical meaning of those modes?
I understand the question, but I haven't thought about these Goldstone modes. I mean, on the basis of Goldstone bosons. So I don't really have the answer of that.
Okay.
Okay. Any more questions? Okay. If there are no questions, thank you, Debodirna.